Hello students, in the present video session, we'll take some examples for Booth algorithm. Booth algorithm requires examinations of the multiplier bits and shifting the partial product. In advance to shifting, the multiplicand may be added to the partial product and the final sum can be computed by adding all the partial product. So we have to consider individual bit q as well as qi minus 1 and we have to compute bit recoded multiplier. So we know that if bit I is equal to 0 and bit I minus 1 is also 0, so then version of multiplicand selected by bit I is equal to 0 into m. Similarly, if bit I is 0 and bit I minus 1 is also 1, and then the version of multiplicand selected by bit I is plus 1 into m. Similarly, if it is 1 and 0, the version of multiplicand is minus 1 into m, and 1 and 1 means 0 into m. So now we'll consider some examples like, so we'll take case 1, that is positive multiplier and positive multiplicand. So now we know that Booth algorithm can be considered for both positive as well as negative multiplicand and multiplier. So we can consider basic 4 cases under Booth algorithm. So the first case is positive multiplier and positive multiplicand. The meaning of this sentence is both multiplicand and multiplier are equal to positive numbers. So we'll take one example. I'll consider m is equal to positive, that is plus 13, and q is equal to plus 9. So we can represent the same number using binary pattern. So I'll write plus 13 as 0, 1, 1, 0, 1, and plus 9 as 0, 1, 0, 0, 1. So now, in the case of Booth algorithm, initially we have to compute bit recoded multiplier. Bit recoded multiplier. For that, initially write q as it is. So I have to consider the sign of the number, that is 0, followed by the magnitude is 9, that is 0, 1, 0, 0, 1, and in order to compute bit recoded multiplier, append one extra 0 to the LSB location. So now we have to check the transition from 0 to 1. The transition is 0 to 1, that means plus 1, 1 to 0, that means minus 1, 0 to 0, that means 0, 0 to 1, that means plus 1, and 1 to 0, that means minus 1. So this is the new value of q, that is plus 1, minus 1, 0, plus 1 and minus 1. So now we'll perform normal multiplication steps. So first we'll consider m. I'll write m as it is. So that means m means we know the value of m as 0, 1, 1, 0, 1 into bit recoded multiplier. We computed it as plus 1, minus 1, 0, plus 1 and minus 1. So now bitwise we have to compute the partial product. So we know that minus 1 into m, that means 2's complement of m. So first I'll write m as it is, that is 0, 1, 1, 0, 1. Take 1's complement of m, that is 0, 1, 0, 0, 1 plus 1, that is 1, 1, 0, 0, 1. So that is nothing but 1, 0, 0, 1, 1. It is nothing but 2's complement of m. So minus 1 into m, that means 2's complement of m. I'll write 1, 1, 0, 0, 1, and later I'll consider 5 extra ones, that is sign extension 1, 2, 3, 4 and 5. So next is we have to compute plus 1 into m, that is 1 into 1, 1, 0, 1, 1, and we have to consider the sign extension as 0. So the next bit is 0, that is 0 into m. So 0 into 0, 1 means 0. So shift it left by 1 position, 0, 0, 0, 0, 0, 0, 0 and 0. So once again the next bit is minus 1 into m. So minus 1 into m in the sense 2's complement of m. So that is 1, 1, 0, 0, 1, 1 and 1. So the last pattern is plus 1 into m. So that is I can write 1, 0, 1, 1, 0 and 0. So now we need to add the entire partial products. So 1, so directly I can write, so this is nothing but 1, 1 plus 1 is 0, carry is 1, 1 plus 1 is 0, carry is 1, 1 plus 1 plus 1 plus 1 plus 1, so that is 5. So I can take 1 here and I can consider carry as 2, 2 plus 1 is 3, I can write 1 and carry as 1, so 1 plus 1 plus 1, so that is 3, I can write 1 and carry as 2, sorry carry as 1, 1 plus 1 plus 1 plus 1, that is 4, so 0 I can write, carry is 2, 2, 3, 4, I can write 0 here, once again carry is 2, 2, 3, 4, so I can write 0 and carry is 1, 0. But I can consider first 10 bits, so that is I can discard this one. So I can say that the partial, after adding the partial product, we can get the value as plus 117, plus 117. So this shows we can multiply positive multiplier and positive multiplicand using Booth algorithm. So we'll consider case 2, that is positive multiplier and negative multiplicand. So we can consider positive multiplier, that is q is positive and multiplicand m is negative. So that means I can consider m that is equal to minus 13 and q that is equal to plus 9. So in binary, minus 13 in the sense 1 0 0 1 1 and q is same, that is 0 1 0 0 1. So that means plus 9. So once again we have to compute bit recoded multiplier, bit recoded multiplier. For that I'll take q as it is 0 1 0 0 1, append the sign, append one extra 0 to the LSB. So now check the transition from 0 to 1. So I can take it as plus 1, 1 to 0, minus 1, 0 to 0, 0, 0 to 1, that is once again plus 1, 1 to 0, that is minus 1. So this is a new value of q, that is bit recoded multiplier. So now we'll consider m into q. So I can write m as m is equal to 1 0 0 1 1 into q means plus 1 minus 1 0 plus 1 and minus 1. So now we have to compute the partial product. We have to compute the partial product of these m and q. So first is minus 1 into m. So first I will take m as it is 1 0 0 1 1. So first take minus 1 into m in the sense 2's complement of m. So 0 0 1 1 0 plus 1. So that is 1 0 1 1 and 0. So this is the value of 2's complement of m. So first I will write here. So minus 1 into m means 1 0 1 1 0 followed by 5 zeros, 1 2 3 4 and 5. So next is plus 1 into m. So that means 1 1 0 0 1, extend the sign bit as 1 itself. Again 0 into m, that is 0 0 0 0 0 0 0 0. Again minus 1 into m in the sense, so I have to take 2's complement of m, that is 1 0 1 1 0 0 0. So once again plus 1 into m in the sense I can write m as it is 1 1 0 0 1, sign extension is 1 itself. So now we have to add the partial product. Add the partial product. 1 plus 1, 1 plus 1, here it is 1, next is also 1, 1 plus 1 is 0, again carry is 1 here, 1 plus 1 is 3, so that is 1 1 0 0, 0, 1, 1, 1. So I can say that magnitude is 117 plus, but the sign is minus. So that is MSB bit is 1. So minus 117, that is 1, 1, 1, 0, 0, 0, 1, 0, 1, 1. So the final product, that is equal to minus 117. So next we will consider case 3, negative multiplier and positive multiplicand. So suppose multiplicand m is equal to plus 13 and multiplier q is equal to minus 6. So I can take m is equal to plus 13. So we can represent using binary as 0, 1, 1, 0, 1, and I can take negative multiplier q as minus 6. So that is equal to 1, 1, 0, 1, 0. So we can take minus 6 and plus 13. So now we need to compute bit recoded multiplier, bit recoded multiplier. For that, write q as it is. So we know the value of q as 1, 1, 0, 1, 0. Append one extra 0 to the LSB and check the transition. The transition from 1 to 1, it is 0, and transition from 1 to 0, that is minus 1. The transition from 0 to 1, plus 1, 1 to 0, once again minus 1, 0 to 0, 0. So this is the new value of q we need to consider while computing the partial product. So now I'll take m as well as bit recoded multiplier q. So value of m means 0, 1, 1, 0, 1 into 0, minus 1, plus 1, minus 1 and 0. So we have to compute the partial product here. So 0 into any number means 0. So I can consider all zeros, and sign extension is also 0. Sign extension is also 0. 1, 2, 3, 4, 5, 5. So next partial product we have to compute it as, it is nothing but minus 1 into m. So minus 1 into m, that means 2's complement of m. So I'll write m as it is. So that is 0, 1, 1, 0, 1. Take 1's complement of that, 0, 1, 0, 0, 1 and plus 1. So we'll get the value as 1, 1, 0, 0, 1. So that is nothing but 2's complement of m. So minus 1 into m, in the sense I have to write 2's complement of m, 1, 1, 0, 0, 1, and the sign extension is negative, that is 1. So next partial product is, I have to consider plus 1 into m. So directly I can multiply, that is m as it is, m 1, 0, 1, 1, 0, 0, 0, 0, followed by once again minus 1 into m. So I have to write 2's complement of m, that is 1, 1, 0, 0, 1, 1, 1. So once again 0 into m, 0, 0, 0, 0, 0. So finally we need to add all the partial products. So it is 0, 1, 0, 0, 1, 1, 0, 1, 1, 1. So that means, so I can consider it as minus 78. So that means 13 into minus 6 is equal to minus 78. This shows how we can perform multiplication operation considering negative multiplier and positive multiplicand. So now we'll consider the last case, negative multiplier and negative multiplicand. So in the case of negative multiplier and negative multiplicand, I'll consider the example m is equal to minus 13 and q is equal to minus 9. So minus 13 in the sense 1, 0, 0, 1, 1, minus 9 in the sense, so I can write it as 1, 0, 1, 1, 1. So now we have to consider the bit recoded multiplier. I'll write q as it is, bit recoded multiplier, bit recoded multiplier, that is, I'll write q as it is 1, 0, 1, 1, 1. I'll append 1 extra 0 here. So I'll check the transition from 1 to 0, that is minus 1, 0 to 1, plus 1, 1 to 1, 0, 1 to 1, 0, 1 to 0, that is minus 1. So now we have to compute the partial product by considering m is equal to 1, 0, 0, 1, 1 and q is equal to minus 9. So that is 1, 0, 1, 1, 1, and you will get the final product as, after performing multiplication operation, you will get the final product as 0, 0, 0, 1, 1, 1, 0, 1, 0, 1. So that is nothing but plus 117. So that means if you are performing multiplication operation by considering negative multiplier and negative multiplicand, you will get the final product as positive number. So that means minus 13 into minus 9, you will get the final product as plus 117. So this shows how we can perform multiplication operation by considering different cases. Either the multiplier may be positive or negative, or multiplicand may be positive or negative. Irrespective of the multiplier m and multiplier q and multiplicand m is positive or negative, the Booth algorithm will compute the final product.